Okay, so good afternoon once again, everyone. So welcome to this live session on 19/11/2025. So uh, in today's session, what we do is first we will see the steps for drawing the root locus. Then for a given problem, so using root locus, how we do the controller design to the design specifications. Okay, so we'll do two steps. First is for going through these basic steps of the root locus. Then we'll consider a problem, how to do the controller design using root locus. Okay, so first is as you know that root locus is a graphical technique. So where the controller parameters varies from 0 to infinity. So this will give you some graphical view of or graphical locus of all the closed loop poles. Okay, so suppose if you have a plant transfer function g of s, okay, and if you have a controller transfer function as c of s, let's say this is y, and here you have the summing point. So the reference is r. Okay, so from here you have this feedback or transfer function as h. Okay, so if you consider this closed loop system, okay, so you could have different functions for this c of s. You could have proportional, you could have proportional derivative, you could have proportional integral, or you can also have PID controllers. Okay, so after adding this controller transfer function, if you find the overall transfer function of closed loop system, okay, so in this it will have this parameters of this controller, right? If it is proportional, we can have only k. If it is proportional derivative, if we have we could have k and kd, etc. So for PID, we'll have all the three parameters. So varying this k from 0 to infinity, how the poles location of this closed loop transfer function will vary. So that's what the root locus basically does. Okay, so let's going through the example. So say we have this open loop transfer function as g of s, and consider the feedback transfer function as h of s as 1. Okay, suppose if we are considering the p controller, it means that this c of s only k. Okay, so then closed loop transfer function. So this is the closed loop transfer function. So would be getting like this. So now from this expression, so we will start with the step one. Okay, so basically in step one, what we do is, given the closed loop transfer function, we will keep that in the events form. Events form is something like this. Okay, so events form gc of s closed loop transfer function, we'll keep it in the g1 of s divided by 1 plus k g2 of s. Okay, so basically our aim and we are looking for the g2 of s, which is nothing but the open loop transfer function. So g2 of s is open loop transfer function. So given the closed loop transfer function, first we have to keep it in the Evans form. Then we are considering this particular g2 of s expression, which is nothing but the open loop transfer function. So what we do is we draw the root locus for this open loop transfer function. Okay, which will give us the locus of all the points for the closed loop transfer function. Okay, so now let us say this now g2 has the poles, open loop poles and zeros. Number of poles here we have n is equal to 4. Number of zeros we have m is equal to 1. Okay, so now n is equal to 4 and m is equal to 1. So now then that is first step. Then second step is, so we'll be finding what are the starting and ending points of the root locus. What are the starting points? What are the ending points? So always we have n is equal to 4 number of poles and number of zeros are 1. So starting points are the open loop poles itself. Open loop poles. Okay, ending points are open loop zeros. Okay, but here we have only one zero. Okay, so in that case, so out of 4 poles, okay, so one pole will goes to this open loop 0 and 3 poles will go to infinity. Okay, so those are the starting points are the open loop poles, ending points are one pole will go to open loop 0 and 3 poles will go to open loop sorry, infinity. That is step 2. Okay, then step 3 we find the real axis segments. Okay, so always the real axis segments is nothing but, so the root locus on the real axis lies in the left of odd number of poles and zeros. It means that here we have the poles location as, okay, here we have the poles location. We have 0 to minus 1 plus or minus z2. Okay, so we have poles location as 0 to minus 1 plus or minus j2. So this is plus j2, this is minus j2. Okay, these locations, these are the poles locations. Okay, so now the real axis segments. So let me check once again. So 0 to plus or minus 1 plus or minus j2. Okay, so the real axis segment says that, here you could see, so it says that, and we have 0 at minus 3. We have 0 at minus 3. Okay, so this point says that, so the root locus lies on the left of odd number of poles and zeros. So what we do is we come from right side and we will check. So if we are here, let's say, so if you check here from this right side, how many poles are there? How many poles and zeros? That number we will check. So at this point we will check. So only one pole is existed on the right hand side of this pole. Hence, this entire thing is part of root locus. Okay. Whereas if you consider any of these points, okay, so the number of open loop poles and zeros will be the even number. Okay, hence the real axis segment between minus 3 to 0 is not part of root locus. Whereas if you consider any of these points, so that number is 5. Total number of open loop poles and zeros is 5. Hence, this is part of the root locus. So this is part of root locus and this is part of the root locus. That's what you can see here. Okay, so total you have 4 poles, 1 0. Okay, so this is part of root locus and this is also part of root locus. Okay, so that is step 2. Okay, next step 3, what we do is we find the asymptotes, angle and centroid. So asymptotes angle is using this formula. So 180 plus alpha 360 by n minus m minus m, where alpha varies from 0, 1, 2, 3, etc. n minus m plus 1. So here in this case, so what is this value? 4 minus 1 plus 1, correct? So that will be 4. Okay, n minus m plus 1. So that will be number of poles we have is, oh sorry, n minus m, it will be 3 I guess, it should be 3. Okay, so then we have alpha is varying from 0, 1, 2. Okay, so that should be n minus m minus 1. Sorry, this should be minus 1. Okay, so in that case, so 4 minus 1 is 2. So 0, 1, comma 2, that is maximum. So alpha is 0, 1, comma 2. So if you calculate these angles by substituting alpha is equal to 0, 1, 2. So you'll get 60, 180 and 300. Then after that asymptotic centroid. So using this formula we find the centroid, that is sigma is equal to sum of the poles minus sum of zeros by number of poles minus number of zeros. So here you are getting 1. Okay. So now here the centroid is 1 and angles are 60, 180 and 300. Okay. Let me take this image. Okay, so what we do here is, so at 1, okay, this is 1, let's say, okay, so you have these three angles. So this one is sigma, okay, you have these three angles. So you have 60 angle, you have 180 angle, you have 300 angle. So always the angles you take in this direction. So 60, 180 and 300. So that is step 4. Okay. Then next step 5, we find the angle of departure as well as the angle of arrivals, because always the uh, root locus starts at the poles. So departures are with respect to poles. Okay. So with respect to the poles, arrivals are with respect to the zeros. Okay. So since we have n is equal to 4, m is equal to 1, so you will have theta d1, theta d2, theta d3, theta d4, and here we have theta z1. Okay. So you have 4 departure angles and 1 arrival angle. So using this formula, you can find the departure angles. So I'll explain for one case. So here you could see we are trying to finding the angle for this P1. Okay, we're trying to finding the angle for this P1. So what we do is, from every other poles and zeros, we find this angle. Okay, so here you could see. So first this angle, you draw the vectors from every other pole and zero also. Okay, then find how much that vector is doing an angle with respect to the x-axis. Okay, suppose for this one, it makes an angle of 180. Okay, it should be clear. Okay, then this one, it makes an angle of this much. Sorry. So this one, it makes an angle of this much. Okay, so this one, it makes an angle 0, whereas this one, it makes an angle this much. So if you know this part and if you know this part, you can calculate this angle. Okay, so always angles we find with respect to the x-axis. So once you have all these angles, okay, so you can find all these angles, means you'll have theta p2, theta p3, theta p4 and theta z1. These are the angles that makes with uh, the pole 1 p1. That is nothing but you're trying to finding theta d1. Once you substitute it, you're getting theta d1 as 0 degrees. Okay, similarly you can find theta d2, theta d3. Okay, then theta d4 final angle. Okay, so these are the departure angles. Similarly for the arrival also you can do the same thing. Arrival angle also you have this formula. So again, since you have only one zero, okay, so this is 0. Again, from all the other poles, so draw the vectors and find the angles with respect to the x-axis. So for this one also something like this. Okay, find the angles. These are the angles that all the other poles and zeros make with this 0. Okay, so then substitute those angles into this, which leads to this equation. We are getting that as 180 degrees. So this problem I have already explained in the previous live session. So for more details, you can also see this, and I'll share this PDF file also. You can verify the angles. Okay, so that's why I'm going a little faster. So we have angle of departure and angle of arrivals. Okay, so then using those, you can draw the root locus. So here you can see. So I'll explain and draw here one more time. Okay, so this is what we have, and we have these sigma here. So three asymptotic angles, 60, 180, and 300. Okay, 60, 180, and 300. So as I said, so if you see these two poles, okay, so what they do is they travel in this direction, right? From here they will meet, and one pole will move this direction. So from this point, one pole will move in this direction, the other pole will move in this direction. That is this part of the root locus. Okay, so whereas you have these two poles, what they do is, so they travel like this, they meet at some point, okay, and from there one pole will go towards this zero, other pole will go to a zero at infinity. Okay, so this is the direction of the poles traveling. Okay, so this is where the poles location, these are at k is equal to 0. So the ending points are at k tending to infinity. Okay, so are there any quick queries, any doubts for drawing the root locus for a given open loop transfer function?
No, sir.
Yeah,
So
so
we can
if we have, yes,
uh,
yes.
we can draw this roughly without even the breakaway points, right?
No, no, I'll explain you in next example how to find these breakaway points. Roughly, you can draw it.
Okay.
Yeah. So because your doubt is this point, this point, this point. How do we calculate? Correct?
Yes, sir.
Yeah. Yeah, yeah. So that I'll explain in next example. You can clearly understand. So first you should get this overview of all these steps. How we are drawing this root locus. Because the controller design, basically we start with drawing the root locus.
Okay.
If you don't have clarity here, it will be trouble. Okay, yeah, so I hope everyone it is clear how we draw the root locus. If you don't have, so I think previously in a live session I have explained the same example. Okay, so with all these steps you can check that video for more details. Okay, so now let us start with the uh, controller design using this root locus technique. Okay, so I'll read this question first. Okay, so in the given question, okay, so unity feedback h of s is given. Okay, unity feedback, just a minute, it is yeah. Okay, so a system is given to us. Okay, feedback control system. So g of s is given. So 1 by s multiplied s plus 2 s plus 4. Okay, so we wanted to design a controller, okay, such that the step response of the closed loop system, okay, so with it should have zero steady state error, okay, and peak overshoot must not be greater than 10%. Okay, so it means our design requirements. Our design requirements are, so first one is the steady state error must be 0. Okay, and the peak overshoot MP, so that must be less than or equal to 0.1. So that means that it should not be more than 10%. Okay, these are design requirements. Now what is the first question? Sketch the root locus of the proportional control system with the proportional control system and argue that it does not meet these specifications. Okay, that is first question. We need to draw the root locus with proportional control system. Okay, and argue that it does not meet the specifications. Second, okay, so propose a suitable PI, PD or PID controller. Okay, indicating how add poles and zeros influence the root locus. So what we do here is mostly, so we will take the PID controller an example and we'll see how this question is being solved. Okay, then we have to find the controller parameters. Okay, so that dominant poles satisfies the requirements. Okay, so let's start with the first question. Okay, so since g of s is given, so g of s h of s equal to, so 1 by s multiplied by s plus 2 s plus 4. Okay, so if you find the characteristic equation, okay, so that is 1 plus g of s h of s equal to 0. So 1 plus 1 by s multiplied s plus 2 s plus 4 equal to 0. So we could get s multiplied s plus 2 s plus 4. Uh, this should be k because we are using the proportional controller. This should be k plus k equal to 0. So if you simplify it, you will be getting s cube plus 6s square plus 8s plus k equal to 0. Okay, right. So now let's start with drawing the root locus. This is our characteristic polynomial, characteristic equation. Okay, so let's start drawing the root locus one by one. Okay, so first one is, what are the poles we have? Okay, poles are s equal to 0, minus 2, minus 4. Okay, and zeros are what? We don't have any zeros. Okay, no zeros. So from here we can write number of poles is 3, number of zeros is 0. Okay, so what is n minus m indicates? That is 3. So what is basically m minus m means? It is number of asymptotes. Number of asymptotes is nothing but what? Number of branches in the root locus. Number of branches of root locus. Correct? So there are 3 branches are there. Okay, first point. Second is, so let's say we are finding the asymptotic angles. So asymptotic angles. So what are the asymptotic angle equations? Theta is equal to, so 2q plus 1 alpha pi divided by n minus m minus n minus m. Okay, so what is q here? 0, 1, 2, 3, etc. n minus m minus 1. Okay, so you will get what? So that is 3 minus 0 minus 1, that is 2. So q you will be getting as 0, 1, 2. So if you substitute here, you will be getting 0 degrees, 180 degrees and 300 degrees. Okay, then let's find the centroid. So centroid is sigma. Okay, let's say A. So sum of all the poles, sigma pi minus sigma zi by n minus m. So 0 plus minus 2 plus minus 4 minus 0 divided by 3. Okay, you'll get minus 2. Okay, so that is centroid. Okay, so now using this, let us draw the first step. Okay, so we have pole set, poles where, so we have pole set 0, minus 2, minus 4. Okay, and we got the centroid as, we got the centroid at 2, minus 2. Okay, the angles are 60. That means this angle is 60 and this angle is 180. Okay, and this angle is 300. This is 60, this is 180. Okay, that is 300. Let me remove this. Okay, so these are the three angles. Clear? Any queries here? Okay, so now, so if you see here, how does the root locus looks like now? So these two poles. Okay, so again, if you start to coming from right side, this will be part of root locus. Okay, and this will be part of root locus. If you start coming from the right side, okay, so if you locate at any point here in this thread, okay, you will see from that point right side you'll have odd number means one pole only. Then if you see here, so hence this is the part of root locus. Suppose if you come here, if you see right side, you'll have two poles. Hence this part is not part of the root locus. Okay. So now if you are anywhere at this point, number of poles and zeros on the right side is 3. Hence this is part of the root locus. Now these two poles, what they do is they travel in the opposite directions. So they travel in the opposite directions like this. Okay. They'll meet at a particular point and one pole will move this direction. The other pole will move in this direction. Okay. One pole will move in this direction, the other pole will move in this direction. Now the question is, what is this point? What is this point? These are the questions. Okay, so that means at which point that will what is this breakaway point? Okay, breakaway point, and at which point the root locus will intersect with the j omega axis. Okay, so first we will find the breakaway point. So or break points, okay, you can call them. So for that what we do is we find dk by ds equal to 0. Okay, dk by ds equal to 0. So again go back and check our characteristic equation. This is our characteristic equation. So from this we can write the function of k. K is nothing but negative of this whole term. So from characteristic equation, okay, so k is equal to minus s plus 2 s plus 4. It can be written as minus of s cube plus 6s square plus 8s. Okay, now if you take ds dk by ds, okay, you will get minus of 3s square plus 12s plus 8. Okay, so take this is equal to 0. Okay, so and if you solve for the roots, you will get s equal to, so minus 2 plus or minus 2 root 3 divided by 3. Okay, so from there you will get s1 as if you calculate it minus 0.846, s2 as minus 3.154. Okay, you could verify that. Then if you see this one, substitute k of s1. Okay, you will get something like 3.079. If you substitute k of x2, it will be as minus 3.079. Okay, but here we look for only k positive, k greater than only the meaningful. Okay, so that's why. So that means what? We consider only this one. Okay, so that is only meaningful. Hence, yes break. Yes break is what? Minus 0.846. This one. Consider only this point. Okay, so at that point, okay, what is your k is? So 3.079. So it means for k is equal to 3.079, Okay, we are getting s equal to 0.846. It means that this particular point is minus 0.846. Is this clear? That is the break point, this point. So this point is minus 0.846. Okay, that is break point. Now question is, what is this j omega cross point, where this root locus cross this j omega axis? Okay, so for that, let us consider this case again. So we are trying to finding j omega axis cross x. Okay, so again consider the characteristic equation s cube plus 6s square plus 8s plus k equal to 0. In this, substitute s equal to j omega. You get what? J omega whole cube plus 6 j omega square plus 8 multiplied j omega plus k equal to 0. Okay, so we already know that. So j equal to root minus 1, substitute that, minus j omega cube minus 6 minus omega square. It should be plus, I guess. Okay, so minus 1 whole square. No. So it should be this. Okay, plus j8 omega plus k equal to 0. Okay, so now in this, if you consider only real part and imaginary part separately, real part is minus 6 omega square plus k equal to 0. Imaginary part is minus omega cube plus 8 omega equal to 0. So from this we can write k equal to 6 omega square, and from this we can write omega square plus 8 omega 8 equal to 0. Whereas here, so we have omega square plus 8 equal to 0. We are looking for the non-trivial. Okay, so how does this one? We have omega is equal to 0 and omega square plus 8 equal to 0, whereas this is trivial. Okay, whereas this one is non-trivial. Okay, so let's look for the non-trivial. Omega square plus 8 equal to 0. So we get omega is equal to 2 root 2, which is nothing but 2.82. Now considering this, what is the k? 6 multiplied 2.82 square equal to 48. Okay, so it means that, okay, so the closed loop roots, okay, so they cross the imaginary axis at s equal to plus or minus j2 root 2, okay, when k equal to 48. Is this clear? So it means this point is j2 root 2. This point is minus j2 root 2. At this, k is 48. Is that clear? Any queries as of now? With this, we finished our first step of drawing the root locus. Any queries?
Wait, sir. I'm just seeing that.
Yeah. So first we consider the breakaway points. This point we are trying to finding that happens when k is equal to 3.079. Okay. Next, j omega cross axis crossing point. So when k is equal to 48.
Here we
Yeah.
like we took S1, so won't we be taking S2?
Which
There would be
one?
two cases. There are two roots of S1 and S2.
Here in this case,
Yeah. So S
yeah,
break
yeah, that's
can
what.
be two. Okay.
No. Here we are looking for k is greater than 0, no? So
Yeah.
that is possible only with this.
Acha, okay. K of S1 and K of S2 I have to find. Okay.
Yes. K of S1 is greater than 0. So that's why we are considering that point only.
So K of
Okay.
S2 is okay. Uh, it's
Negative.
just like okay, negative. Yeah, fine.
Yeah. So
So
we don't
we
consider
will
S2. We are
take K of
considering only
S1.
S1.
Okay.
Yes.
We will
Okay.
take S1 and
So
then what about the other slide? Then I have a doubt in the other slide.
this one.
No. Afterwards, after this.
No.
Oh,
We are ready to
this is
go.
last.
So here we are finding the J omega crossing point.
Okay.
Okay.
Hmm.
Yeah. So finally, this is our root locus. Okay. So now this is root locus. What we are
Yeah.
doing? We are doing with uh, uh, proportional controller. Okay. Now come back to the question. So in the question first part, sketch the root locus of the proportional control system and argue that it cannot meet the specifications. Okay. Now what are
Okay.
the specifications we have? Okay. So what are the specifications we have? We have already listed them out. Okay. The design specifications are these two. So the steady state error should be 0 and the peak overshoot must be less than 10%. Okay.
Yes.
So now, so look at our first question. So, okay. So with the proportional controller, we need to check whether it actually is proportional controller satisfying these design specifications or design requirements or not. Okay.
Okay.
So yeah. So first what we do is, okay, so let's start with the first one. Okay, so ESS. So we know that ESS is nothing but limit S tending to 0 S E of S, where limit S tending to 0 S multiplied E of S, yes, expression is R of S divided by 1 plus G of S H of S. Okay, so you can multiply because we are looking this one for the step response. Okay, limit S is tending to 0. S multiplied R of S is 1 for a step response. So 1 plus G of S H of S is K by S multiplied S plus 2 S plus 4. Okay, so this can be written as these two gets cancelled. So this can be written as limit S is tending to 0. S multiplied S plus 2 S plus 4 divided by S multiplied S plus 2 S plus 4 plus K. Okay, so if we check this one, this goes to 0. Okay, so it means that, so the first one is satisfied. So with the proportional controller, first one is satisfied for any K. Okay, now let's check the second one. So second one is the peak overshoot. Okay, so peak overshoot, we know already that MP is, so the equation, if you remember, e power zeta pi root over 1 minus zeta square, let me write it like this. Okay, so this is e power, so MP equal to e power multiplied by 100. Okay, so here our design requirement is MP must be less than or equal to 0.1. Okay, so that means e power minus zeta pi by root over 1 minus zeta square into 100. Okay, so must be, let us start with at least at max it is 0.1. Okay, so suppose if you take ln on both these sides,
Sir, 100 won't come, sir.
sorry, yeah, because we wrote it in percentage. Yeah. Okay, thanks. So now if you take ln on both these sides, So here you will get pi zeta root over 1 minus zeta square. You'll get this value as 2.3026, including that minus negative sign also is taken care. Okay, so you can take 2.3026 divided by pi. Okay, if you take square, you'll get like zeta by 1 minus zeta square. Okay, so from here you could get zeta square, if you solve it, is almost equivalent to 23496. You will get zeta as 0.591. So that is the minimum zeta we need. Okay, so that is minimum zeta, minimum damping ratio we need, that makes your system does not make the peak overshoot more than 10%. Okay, so that is first point. So we need to have that zeta requirement is 0.591 minimum. So more than that also fine. Okay, also we are looking for the settling time. Okay, so settling time, so if you look for the 2% tolerance, okay, so what is it? Ts equivalent to 4 by zeta omega n. Okay, so in this we already know the zeta value. Let us try to find omega n. Let us try to find the omega n here. Okay, so we know already the characteristic equation. Okay, so s cube plus 6s square plus 8s plus k equal to 0. Okay, so let us try to match this one with the standard cubic representation. So what is that cubic representation? We have standard second order is, so s square plus 2 zeta omega n s plus omega n square. We know already this. So if you wanted to put this one into standard third order or cubic representation, so we will multiply with some pole P3. Okay, now if you have these 1 and 2, okay, so if you match the terms, so match the similar terms, okay, so you can check them. Okay, so for already we know that zeta is equal to 0.591. Okay, so if you match the similar terms, we will be getting P3 as minus 4.57, and we will get poles as, we will get dominant poles, okay, as minus 0.715 plus or minus j.976. Okay, and we get k value as close to 6.69. Okay, so what we are doing here is we are considering our characteristic equation, okay, and considering the standard cubic representation, comparing the terms for zeta which we already know. So we are calculating P3, this dominant pole, for k also. Okay, so we generally know the equation, generally know this expression zeta omega n plus or minus omega n root over 1 minus zeta square for second order system. Correct? So now, so what happened here? Finally, this proportional controller, so proportional controller, so it is it can meet so MP less than or equal to 10%. Okay, for so zeta is close to 0.591, but because we can able to get that, But so what is the real part of this? This is the real part. Let me write it. This is the real part. Real part is 0.715. That is nothing but zeta of omega n. Okay. So settling time, what do we have? Settling time is zeta by settling time is, what is the equation for settling time? So this is 4 by so this is 4 by zeta omega n.
Sir, is
So
there any tolerance is given 2%, 5%? So,
sorry,
like,
this one in the question itself.
so it's 10% is given, but like TS we take
No,
when
no, no.
tolerance.
10% is peak overshoot.
Okay, so like for settling time, there is one formula like 2% we take 4 upon zeta omega, and then
Yeah,
if it's
yeah, yeah. This is 2%.
so how
This
we
is
took
2%.
2%?
No, not necessarily. We can go for 5% also.
Okay,
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 that always depends upon the system. What is the tolerance from the reference slide you wanted to have? Okay, so in
okay,
this case, we are taking this 2% case. Okay, so
okay.
4 by 0.715. Okay, so
Yeah.
which will give you close to 5.6 seconds. Okay, so now here the settling time is almost 5.6 seconds. Okay, so this one. Okay, here you can able to, this proportional controller can be able to meet this peak overshoot, but settling time is 5.6 seconds. Okay, it means that, so this is a little slower. Okay, system is little slower. Okay, so that's the conclusion. So here the first question, we need to draw the root locus with proportional controller and check whether it is meeting the requirements or not. It is meeting the requirements of, so ESS is becoming 0, the steady state error, and for zeta is equal to 0.591, we can able to get peak overshoot as 10%, but when you calculate settling time, it is giving 5.6 seconds, which is little slower. It means that it is settling to 2% tolerance at 5.6 seconds, almost very high. Clear? So
Sir,
that's the first question. Yeah.
how do you decide it is little slower, sir? So what should be the ideal value?
No, not like that. Okay, 5.67 is literally, I mean, much very high. Suppose if you
Based
see
upon
your
our
RL
settling
circuit or
time,
RC circuits, no,
based
if you
upon
see your
settling time,
RL
we are
and no, settling time we are getting as 5.6 seconds. Okay,
okay.
her question is how we are deciding 5.67 is very high. Okay, so that's why I said it is little slower. Okay, so generally the systems 5 seconds means it's somewhat considerably high. Why?
Yes.
Because suppose if you consider your RL or RC circuits, okay, so
Mhm.
their studies, they reach the steady state within a fraction of seconds.
Within fraction of seconds. Yeah, 0.6.
Yeah,
Yeah.
yeah, it may not be even 1 second also. If you see
Mhm.
their curves, okay. So here
Yes.
5.6 seconds is very high. Okay, suppose if your
Okay.
RL circuit or RC circuit, 5.67 is it's like I mean orders. It is very high,
Yes. Yes.
considerably. Okay,
Yes.
so now here, since we don't know the physics of any physics of the system, what this system is exactly. Okay, let us consider this is system is little slower. Okay, that is first question. Next, so we need to propose either PI, PID or PID controller. Okay, here we are considering PD controller. Okay, so to indicate how the added poles or zeros influence the root locus. Okay, let's start with that. Okay, so let us say that we are trying to adding a zero, right? So we add a 0 using PD controller. Okay, so let's take C of S as KC S plus A. Okay, so where KC is some gain, yes, and A is the 0 we are trying to add. Okay, so basically why you wanted to add 0. Okay, so there are 2 points. First point is if you add a 0, okay, so it pulls the root locus left. It pulls the root locus left. Okay, if it is pulling the root locus left means you will get fast settling time. You will get fast settling time. That is first point. Second point is, so if you place the 0, whatever the 0 here A, okay, so near the plant pole, let's say your plant has this S is equal to -2. Suppose if you take S is K is equal to -2. Okay, so this would lead to what? This would lead to pole 0 cancellation. If you lead to pole 0 cancellation and tries to neutralize the situation. Okay, these are the two advantages. The first one is it pulls the root locus to the left, more left. Then so by you can add a 0 nearer to the S is equal to -2, so which gives us the flexibility of pole 0 cancellation. Okay, now let us say, so let us say we are choosing let, okay, so choose A is equal to 2. A is equal to 2. Okay, so now the open loop transfer function will become like this. So Kc S plus 2 divided by S multiplied S plus 2 S plus 4. Okay, so that is nothing but Kc divided by S into S plus 4. Okay, so this gives us, okay, so this gives us second order dominance. So this gives us second order dominant poles. Okay, so dominant behavior, okay, so that we can shape easily. That we can shape easily. That is one of the advantage. Okay, now, so what is our main thing here? So we got our TS settling time as close to 5.6 seconds. Okay, we wanted to reduce it. That's our aim. Okay, so since we wanted to reduce that, okay, so our aim here is, so designing for faster response with, we don't want to compromise on the overshoot also. Overshoot less than or equal to 10%. Okay, so what this basically 10% requires, our Z must be 0.591 minimum value. Okay, so so along with this, so this is one. Along with this, what we need is faster response also. We need faster response also. Now, for that reason, what we do is, let us try to choose real part sigma as -2. Okay, so previously, what do we have here? Sigma as -0.715. Okay, in place of that, we are trying to choosing sigma as -2. Okay, so what does basically that -2 means? Sigma omega n, that is 2. Okay, so since you know already zeta, so omega n is 2 by zeta, which is nothing but 2 by 0.591. You will get so 3.384. Okay, so and we know that the poles are, how does it looks like? Minus zeta omega n plus r minus j omega n root over 1 minus zeta square. So in this we already took omega zeta omega n as 2. Okay, what is imaginary part? Okay, so imaginary part is nothing but omega n root over 1 minus zeta omega square. If you substitute, you will get 2.73. Okay, so finally, what are the poles? Then the desired dominant poles. What are the desired dominant poles? S is equal to minus 2 plus or minus j 2.73. These are the desired dominant poles. Okay, so now again, so these are the poles which we wanted to place. Okay, so now, so what is the function we took? So the C of S we took as KCS plus A. Okay, KCS plus A. Okay, so now what is the modified closed loop transfer function? By including this modified closed loop characteristic equation. Okay, so that is nothing but S cube plus 6s square plus 8 plus kc multiplied s plus kca equal to 0. Okay, so again, so take the standard cubic. Okay, so what do you take? S plus p3. So this is s square plus 2 zeta omega n s plus omega n square. Okay, so again matching will give us, if you match the parameters, match the terms on both these sides, so you will get p3 plus 2 zeta omega n is 6, 2 zeta omega n p3 plus omega n square is 8 plus kc. Second one, last one is p3 omega n square is kca. Okay, so if you calculate them, so you will get the result as p3 as almost 2, kc as 11.45 and a as 2. Okay, so finally what is our C of S is going to be 11.45 S plus 2. 11.45 S plus 2. So this is the PD controller. This is the PD controller. Okay, so with this PD controller, what are the poles we will get? Okay, so we will get dominant poles as S is equal to minus 2 plus R minus J 2.73. Okay, with this controller. Okay, so with these poles, so now from this we can write the damping ratio. Damping ratio zeta as 0.591 for the same damping ratio, and overshoot we will be getting as same 10% only. Okay, and what is the settling time finally? Settling time Ts equivalent to 2. So 4 by zeta omega n, nothing but 4 by 2. So that is almost 2 seconds. Okay, so this is much faster. This is much faster, 2 seconds. So previously, let me write it as a summary. Okay, so first with the proportional controller. Okay, second with the PD control. Okay, so proportional controller. So MP is satisfying, which is 10% at max. Then TS is 5.6 seconds. So slow. Okay, and K is, what is the K value? 6.69. Whereas here C of S is 11.45 S plus 2. So here the dominant poles are what we are getting. So minus 2 plus R minus J 2.73, this one. And so TS is 2 seconds. This is actually faster. And in both the cases, we are getting the error is steady state error as 0. Okay, so this is how it looks like. Okay, so basically what is happening is, if you consider C of S is this expression and draw the root locus again. Okay, so your root locus with the same shape of the root locus, it will be shifted to the left. Okay, any queries on this? So this is because of the PD control, where only P control alone. So it is meeting the requirements, but it is giving a steady state settling time of 5.6, which is very slow, which is literally slow. So whereas once you get this PD control, so the settling time is 2 seconds, which is a little faster. Okay, so that is the main thing. So the thing what we are checking here is proportional versus PD control. Okay, so here the PD control expression is C of S equal to Kc multiplied S plus A. Okay, that's the expression we consider. Okay, so in reality they are not actually realizable. Okay, they are not actually realizable. So with zeros alone, that's why what we do is, so we take the controller as some K multiplied S plus A by S plus B. So they are something like S plus ZC by PC. Okay, so this expression also called as the compensator. Okay, so which will have both PD and PI controllers. So there will be variations between ZC and PC. That the problems related to these compensators we'll see in the next live session. Okay, so basically these not in reality these kind of PD functions are not realizable. Controllers are not realizable. Okay, not possible to provide them practically. So that's why we go for the compensators. So what exactly these compensators? How can we solve these similar kind of problems with compensators? So with lead compensator, lag, and also lead lag compensator. So we'll see in the next live session. Are there any queries in this problem?
No, sir, it's clear.
Yeah, so I'll share these lecture notes. So please verify everything along with these calculations. You will
Yes.
understand the major difference when we take the proportional, when we take the PD control. Okay. Yeah. So we'll stop here. Thank you.
Thank
Sir,
you.
we will meet on Friday. No?
Yes. We'll meet on Friday.
Okay.
Yeah. Thank you.
Sir, you will be taking or ma'am would be
No,
taking?
Friday I'll be taking.
Okay, sir. Yeah.
Yeah. Okay.
Thank you, sir.